Welcome everybody. So we're gonna solve past paper in the organic part, the year of 2016, October, November, variant 1. So let's start with the question 4 in here. It says that you have in each section of this question an organic compound is shown. For each compound, give its name. Okay, and then we will answer the questions about it. So let's start with the first one, which is A. We have to name this compound. So first of all, you notice that you have a double bond in here, and we're supposed to have alkene, by the way. And how can I solve that? We will start counting the number of carbons from the closest double bond. So we notice that we have 1, 2, 3, 4, 5, 6. Why didn't count this? Because this is a branch. So how did we know that? If you start reading it from the left in here, you will notice that we have CH3 first, and then it's followed by CH2, and then it's followed by CH. We just noticed that the carbon makes 4 bonds. So if it has CH, okay, and we have another CH2 from the other side, I mean this, and we have C double bond, then we're supposed to have another bond for this methyl group, and this is for methyl, and that's why we have methyl group in this carbon. If you want to, let's say, to identify, or let's say understand it way better than this, you can write it in the displayed formula. So you can write C, and you have C, and this is another C, you have 2 carbons, and you have another C with H in here, we have CH3, okay, and you have a double bond here, C double bond, it has hydrogen, and here we have C with another hydrogen and CH3. And if you just like to count the number of atoms, we will start counting according to the closest double bond. So we say 1, 2, 3, 4, 5, 6. Then we're supposed to have hex, okay. And we notice that we have a branch on the 4th carbon, which is in 4. Okay, we can say 4-methyl, okay. And we notice that this is hexene, and the position of the double bond is in the 2nd carbon. So your answer is 4-methyl. We don't make a space. Hex 2-ene. Okay, let's go to double I. The double I question is related to the answer in here. Just put in your mind. And it says that this compound shows stereoisomerism. So once we say stereoisomerisms, you have to put in your, we're dealing with cis or trans or optical isomers, all right? So this question says what is, or let's say define the stereoisomerisms. So we have keywords. By the way, the question has only 1 mark, but the recent years gave on this questions 2 marks, and you have to focus on what? You have to say molecules of same molecular formula and structural formula, but different in arrangement in space. Okay. The question says state and explain. So you have to state with a short answer, and then you have to explain this short answer. And you just notice that you have 4 marks on this question. So let's go again. It says that state and explain how many stereoisomers of this structure there. So look at this structure in here. So I will draw it like this. You have CH3, CH2, CH, and you have methyl. I just like to draw it in this case so you can, let's say, deal with it in a 0 way. And here we have C and CH3. Okay, yeah, it's the same. So look at this. When we say stereoisomers, we're dealing with opticals and geometricals. So we're supposed to have both or one of them. According to what you see in here, you notice that this is the double bond in here has hydrogen, it has hydrogen, and has methyl group, which is in here, which are different groups, and this is good. And if you look to this in here, you notice that it has hydrogen in here, and you have C, H, it has methyl, and you can complete the stuff CH2 or CH3.
Actually, I didn't draw that in intentionally because it could be cis or trans. So once you have cis and a trans, okay, we have geometrical isomer in here because we have different atoms are bonded to each carbon, and this is the first condition. And we notice that do we have a chiral center or let's say mirror images in here? If you look at this carbon, no, because we have 3 symmetrical atoms. Here, no. But if you look at this carbon, you notice that it's bonded to CH3, and we have CH, and we have CH2 in addition to H. So we're talking about, let's say, a chiral center. Yes, we have a chiral center in here. So we have chiral center and we have geometrical. Metrical, I mean cis and trans. So how can I guess and deduce the structure? I want to give you a very good idea that works for all of this stuff in here. You'll definitely say like, if you have cis and a trans, you will say like cis and a trans, and you have the 2 mirror images, right? And then you say like the total will be 4. But actually this method, it could work with 4 number, but actually it doesn't work for a greater number of geometrical isomers. So you can put the probabilities. So first of all, you could have in the same compound, you could have C double bond, and you have the chiral center. So suppose that we're gonna talk about, let's say call it a trans, okay? And for this mirror images, it could be clockwise or anti-clockwise. So let's call them, for example, like left and right. By the way, the optical isomers have another names which are S and R, but these things, or let's say these topics will be covered in the HU, so there is no need to know about these now. So you could have clockwise or anti-clockwise. You could have trans with L or trans with R, okay? And you could have cis with L and cis with R. So you have 4 probabilities. You could have a trans with L or trans with R or cis with L and cis with R. So the total number will be 4. How did you know that you have 4 stereoisomers? First of all, what to do according to the Mark scale. Yeah, the short answer here is state how many stereoisomers you have to say you have 4 stereoisomers. 2 from the cis and the trans, and 2 from the mirror images, okay? In total would be 4, okay? And then you have to tell me what is the second mark. This is first mark. The second mark, you have to tell me you have a double bond and it has another mark. When you say you have a double bond, you're talking about forbidden rotation around the CC double bond in this case. And that's why you have geometrical isomers. And the second mark that you will take, you have to tell me about, you have 2 different groups, 2 different groups on each double bond carbons. Okay, so this is the third mark in here. And for the chiral centers, you have to tell you have 4 different groups bonded to carbon. And that's why you will have optical isomers. Okay, and that's it. So you will have a first mark, which is about the short answer in here. The second mark when we say you have a double bond, and that's why you indicate the forbidden rotations around the CC bond. And you have to say that you have 2 different groups on each carbon. These are different, okay? These are different from each other and different groups bonded to each carbon. Okay, let's go to branch B, I. You have a compound and the question needs to name it. So how can I name a compound? First of all, the beautiful way is writing this in clearer structural formula. So you can say like you have double bond carbons, CC, and you notice that this carbon is bonded to 2 methyl groups. So this is CH3 and this is CH3, and the same thing here, okay, CH3 and CH3. All right, so first of all, I just want to clarify something. You notice that we have groups around each carbon which are identical. So in this case, we can say we have no cis and trans isomers, no geometrical isomers. Okay, but it's not our case. So how can I name this compound? First of all, the first step is finding the longest chain that you have. So we noticed that we could work like, yeah, like this is the longest chain. Yes. All right. So if I want to start counting the numbers, let's say 1, 2, 3, and 4. So longest chain here is bute. I just want to do that in here. Yeah. So the first thing we have bute. And we notice that if we talk that as a long chain and you start counting it from here or here, according to the closest double bond, it's equally from all sides. You will notice that you have methyl group on the second carbon, okay, and another methyl group on the third carbon. So we could say that you have 2, 3 dimethyl, okay. And you notice that the presence or position of the double bond is in the second carbon, then it's 2-ene. Okay, so we can combine all of these words together and then we can find the answer. So the question will be 2, 3 dimethyl. Okay, done. No space, bute. And then the position, which is 2-ene. So this is the answer. All right. Let's go to double I. It says that it draw the skeletal. Look at this. This is a skeletal, skeletal formula of organic product of the reaction of this compound with cold dilute acidified. So first of all, you have to remember something. Once we use this reagent, we're talking about the oxidation process, okay? And this oxidation is, let's say, does not fragment, okay? I mean like the MR of this compound won't get smaller as a result of the oxidation, okay? So this is not the idea in here. Okay, so if you have this compound, just want to draw it in here. You have C, double bond C, you have methyl groups on each one. You can do that, let's say, in the structural formula, and then you can translate it later on to skeletal because, yeah, it's easier to deal with. So once we add these reagents, acidified KMnO4, and this is gold and dilute, yeah, what will be the answer here? Put in your mind, once you use such a compound, you have to add the OH group on here and in here. Okay, but the first step is breaking the double bond. So the compound will be the same as this. You have C, you break the double bond, and you will have OH groups on each carbon. So we can say you have the OHs in here, and then you have the rest of the compound, like methyl groups on the other carbons. Okay, so this is the new thing that you will add. OH groups on each carbon because you have mild oxidation conditions. So you draw that in this case, but the question needs to be in skeletal. So once you do that in terms of structural, you can translate it to skeletal and you can erase all of this stuff, okay? How can I do that in terms of skeletal? You can do that, let's say, like this, and this, and this, and you have OH. Guys, put in your mind the hydrogen in the skeletal formula. If it's bonded to different atom rather than carbon, you have to draw it. Okay, some of the answers that I saw, some of people like using OO because they consider the H atom does not include in the skeletal formula. But once the H is bonded to different atom regardless carbon, then you have to draw it. So this is not correct, okay? You can draw it another way, like and you can count the number of carbons, like 1, 2, 3, and 4, like 1, 2, 3, 4. And you just notice that on the second and the third carbons, we have two substituents. We have OH groups and methyl groups. So here we can draw it like this and like this. All right. It's not correct to do it like this. You have to put one in up. No, it's not correct at all. Once you have two substituents in the same carbon atom, you have to draw them like the thorns, right? Okay. Here we have two substituents. One of these is OH, and here one of these is OH. It doesn't matter if you put the OH in here or in here. It doesn't matter. And the methyl group remains as it is, like this only. Okay. So let's go to the triple I. It says that name the organic product of the reaction in this compound with hot. Look at this, it says hot concentrated acidified manganate. So we're doing here the opposite, hot concentrated acidified. So in this case, the compound will be fragmented to different parts. I mean this compound. How can I deal with that? All right, so you have C, and it has CH3, 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 CH3. Once you make oxidation, under these harsh conditions, the bond will be broken from the middle. In put in your mind, the question is asking you about the organic compound, okay? It says that the organic product. It doesn't say organic products, okay? Which means that your compound is symmetrical. This is symmetrical. First of all, you will break the bond, and then you will add oxygen in here. So you will have C, you will draw this part in here as it is, CH3, CH3, and you have double bond in here all. So this is the compound that you have, and it's called propanol. IV. The question says, draw the structure of part of a molecule of addition polymerization formed from this compound, showing exactly 3 repeats units. So first of all, you have to go to the compound. This is related to this one here. Okay, so first of all, you're going to go and draw the monomer of your compound. So the compound here, which is the monomer, like CH3, 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 CH3. Okay, so once you make a polymerization reaction, you will break the bond in here, which is pi bonding. Okay, you break pi bond and reform a new sigma bonds. So once we do that, you will change that to C and C, and you will have CH3, 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 and CH3. You break the pi bond, and then you will make another sigma bonds, and then you will put them in brackets like this. So in this case, we can say this is a repeat unit. But wait, the question needs to draw 3 repeats unit. So you have to repeat this 3 times. How can I do that? Simple. Put in your mind, this is a unit. This is a unit. I want to draw it in terms of 3 repeat units. Put in your mind, you're talking about repeat units, which means that you have to put them in square brackets and just show me this bond. So let's start with the first one. We have C, C, you have, this is the first one, okay? And then we have the second one, and we have another third one, okay? And then we have to put the, let's say the makeup on these issues. So you notice that you have CH3, CH3. Put in your mind, the question is asking about the structure, and generally you're going to draw the structural formula of the compound. So this is the correct answer. The repeat units means that you have to draw them in terms of square brackets. So this is the first repeating unit, this is the second one, and this is the third one. Okay? Okay. So let's jump to the next one. Look at this. All right. The question says you have a compound and we have to name this compound. So the first thing that you could do is you have to analyze this compound. You have CH2 in here. Once you find something that looks like CH2, put in your mind, we don't have geometrical isomer in this case because you have identical atoms on the same carbon. And you have C, okay, that is bonded to 2 methyl groups. So we have CH3 in here and you have another CH3. So this is the beautiful thing. First of all, you have to find the longest chain that you have. So we can say like, yeah, we can do this is the longest chain. All right, and the second thing, you have to start counting from the closest double bond. The priority is for the double bond. So we can start counting from here. For example, 1, 2, 3. No, it's not correct at all because it's far away of the double bond. So if you start counting from here, we are closer. 1, 2, and 3. So first of all, you can say this is a pro, okay? And it's 1 in, okay? This is a pro, okay? And this is 1 in. And you notice that you have a beautiful methyl branch on the second carbon, and it will be like 2 methyl
2-methyl. So we combine all of this stuff together and then we will have the answer. So let's go in here. So if you combine them, you will have 2-methyl. Okay, 2-methyl. All right, no space, prop. Okay, 1-ene. Okay. Put in your mind another thing to discuss in here. Sometimes this type of compound, or let's say this is a certain type of compound, it's called methyl propene, because you have only choice to put the double bond on the first carbon. It's only 3 carbons, right? So it's always in the first carbon. So there's no need to put this, for example. And if you have methyl group, it won't be in the first carbon, because if you put in the first carbon, it will be butene. So it's definitely in the middle carbon. Both are correct. This is true. Okay. Let's go to the double I in here. How can I deal with such reaction? So first of all, it says that complete the mechanism for the reaction of this compound with hydrogen bromide, HBr. Include all necessary Curly errors, lone pairs, charges, partial charges. So let's start with each single detail in this compound. Put in your mind you have 4 marks and it's easy to take them, literally. Okay, so first of all, you have to look at this compound and you just notice that you're gonna have, or let's say your compound will be ended in a halogen alkane, and this is tertiary. Okay, this is tertiary. So you'll notice that the double bond in here, okay, you will have hydrogen and bromine, and one of these atoms will bond it to this and this. So you have to determine first which of atoms will be bonded to each other. You will notice that the bromine will bond to the carbon in the middle, okay, to form tertiary, which is more stable, you know. Okay. So first of all, I have to assign the partial charges. Here we have partially positive, and here we have partially negative, and it's for sure yeah. And then you have to show me the direction of errors. The double bond is an area of high electron content, so it will attack the partially positive hydrogen, and you will notice that it will look like this. So the first step here is attacking the partially positive hydrogen. And then we will have a heterolytic cleavage or fission of this bond, and the electrons in the bond will go to the bromine atom. The 2 electrons in this bond, look at this, what will happen here? They will change the bromine to be, look at this one here, it will have 2 lone pairs. So these are the lone pairs that you have to show. These are the lone pairs that you have to show. Okay. So as a result of this reaction, you will have a carbocation. In this carbocation, what will happen here? This hydrogen, okay, will be taken to this carbon in here. How did we know that? If you go to the product, you will notice that it was CH2 and then it becomes CH3. So for sure, the hydrogen is bonded to this carbon. Okay, just remove of these arrows, I don't care about them. Okay, so you will have CH3, I mean this, okay, that is bonded to CH3 in here. You will have a positive carbocation, and here we have the rest of the compound. Okay, so this is the formation of carbocation. And put in your mind, we have carbocation here because it's tertiary and it's more stable than primary and secondary. And then what will happen? You will draw the curly arrow here. This lone pair, or let's say this bromide, okay, will attack the positive carbon, and it will like this. Guys, put in your mind, you have to be aware of the head of the arrows, okay, the head of the arrows. So according to what you see, did you draw the curly arrows? Yes. Did you draw the lone pairs? Yes, here the lone pairs, you know, and the charges. Yes, I mean like this is a charge, and the partial charges which are in here. Yeah, then if you do all of this stuff, you will take the 4 marks, and it's not that hard. Okay, let's go to the last question. The compound that we have is called 2-bromo-methyl propane, which is this one. It says that this compound is the major product of the reaction, which means that we have minor product. Okay, the question says that we have to explain why we have this compound as a major. As we told you that you will have tertiary carbocation, and the tertiary carbocation is more stable than primary and secondary. So what are the things that you have to put in your mind? Okay, you have to put in your mind you have tertiary carbocation, okay, which is more stable than what? If you have this compound, you have two products if you have this reaction, by the way. Okay, I just want to erase all of this stuff in here. I just want to clarify a little bit. You could have the H in here could attack here or in here. So we talk the idea when the H attack in this area, but what happens if we attack it in here? You will have something like CH3, C, and this carbon in here will take another hydrogen. It becomes CH with methyl, and you will have CH2, and you will have a plus sign here. So in this case, you will have a primary carbocation, and the primary carbocation is not stable at all. So you say like it's tertiary carbocation, and it's more stable than primary, and you will take a mark on this answer. And the second answer that you have to clarify why, because we have something called positive inductive effect is greater in tertiary carbocation, okay, that stabilizes the carbocation, and this is the second mark you have to talk about. And as a result of that, it will reduce the charge on the carbocation. I just want to explain that in terms of what is happening actually in here. If you have a carbon plus and it has alkyl groups like, for example, like CH3, for example, put in your mind in this case, we have alkyl groups and they have electrons. So the carbon here, which has a positively charged species, feels, let's say, the charge makes the carbon unstable, but as a result of the three alkyl groups, it makes, or let's say, decrease the effect of these charges. And the reason behind, because the alkyl groups are electron donating, okay, and that's why they decrease the effect of the plus charge on carbon, or let's say carbocation, and that's it. Let's go to the question 5, and it says that you have a sequence of reaction is shown starting with alcohol, most likely it's a propanol. All right, and as you can see, we have the scheme of the question. The question A says, draw the skeletal formula of alcohol. CH3, H7OH. Probably you will have something like CH3, CH2, CH2OH. Okay. And the question is, how did we know that the position of OH group is on the first carbon? We could have something like this. Why not? CH3, CH, and we could have the OH here and then CH3. So how did we know that it's on the first carbon? The answer is very easy. If you look at the scheme in here, you will notice that one of the reactions of this alcohol producing the aldehyde. This is the functional group of aldehyde. So once you have aldehyde, then the OH is in the terminal part of the molecule. Okay, so if you make oxidation for alcohol, in this case, you will have aldehyde, but if you make oxidation for this, you will have ketone. And that's why we can say this is the compound. Okay, but the question says that we need to draw the skeletal formula of the compound, skeletal, okay? So you will draw that in terms of 1, 2, 3, and you will have OH in here. So this is 1, 2, 3, and this is your formula. All right. Let's go and see the question. State the reagents and conditions needed for reaction 1. Let's go and see what is reaction 1. Reaction 1 here, when you have alcohol and then you will change it to what? You're changing to carboxylic acid. So definitely this is oxidation reaction. So the products, or let's say the reagents that you will have, definitely you will use acidified, okay, chromate, K2Cr2O7, okay, and you have to apply, the conditions, heat and reflux, okay. So you have 2 marks, you have to identify the reagents and then the reflux. Let's go in here and see, state the reagents and conditions needed for reaction 2. Let's go and see what is reaction 2. You will notice that you have OH that changes to aldehyde. And by the way, this is oxidation. But if you remember something, if we have oxidation, first of all, you will have aldehyde. Okay, and then you separate the aldehyde before changing it to carboxylic acid by distillation. So you have to say something about the distillations for the conditions. This is a must. Then you will say you will use acidified, the same as this one above here, but we did a reflux in this case. Okay, you have to say K2Cr2O7, which are the reagents, but the condition needed here is heat and distillation. It says that name P, organic product of reaction. Let's go and see P. You have alcohol and you have carboxylic acid. It's composed of 3 carbons and it's composed of 3 carbons. So probably it's ester, and this reaction is condensation. And you can draw it in this form. You have CH3, CH2, C double bond, OH. Okay, I just remove, yeah, and you have CH3, CH2, CH2, OH. Then if you want to combine this, you will take the whole compound like this and just put it in here instead of the H. And then you will have a compound that looks like CH3, CH2, C double bond, okay, O. I just want to clarify it well. Yes. And you have O, CH2, CH2, CH3. So according to name this compound, we take this part first, which is a propyl. Okay, propyl, and then here we have a propanoate, propanoate. So the compound that you have, ester, okay, is called propanoate. And that's it.